Okay, today I want to start a discussion about electronic drivers for stepper motors. Okay, and before discussing the circuits that are typically employed to say drive and supply power to the stepper motors, is necessary to provide to all of you a very short brief introduction to the way these kind of motors are operated, their construction, etc. Okay, so this today is an overview of stepper motors operation and behavior classification, etc. So let's start with the name stepper motors. Sometimes they are also known as simply step motors, sometimes stepping motors. Okay, in literature you can find different kind of name. Basically, the name includes the word step because this kind of motors rotate through fixed angular steps in response to input pulses received by the controller. Okay, so there are a system that they receive pulses, okay, with given frequency, and for each of these pulses, the shaft of this stepper motor rotates through a fixed and defined step, which is an angular, okay, definition of the rotation. We have to say that recently there's been a widespread demand for this kind of motors, since the popularity of this stepper motor is due to the fact that it can be controlled directly by programmable controllers, microcontrollers, without very complicated closed-loop features. Okay, typically they are well suited for a situation when you need precise positioning or application which you require precise speed control. Okay, for example, automation systems, etc. So the features of stepper motors is that the shaft rotates in a series of discrete angular intervals that are called steps. One steps being taken each time a common pulse is received. Okay, there is exactly a one-to-one relationship between the electrical pulses received by the controller of the stepper motor and the step which is obtained at the shaft of this motor. This makes this motor, as I said before, very well suited for open loop position control. Since there is this one-to-one relationship, okay, I exactly known which is the angular position of the shaft of these stepper motors after a defined number of pulses applied to the input, okay, without the need for, say, closed loop position control. Okay, basically it can be employed as an open loop position control system. Okay, what is the kind of torque that can be developed by this kind of motor? Is a wide range of torque because it can be, say, as low as I don't know, 1 micronewton per meters. Typically, for the very small stepper motor, you can find in the wristwatch. For example, they are very few millimeters dimension of this stepper motor that can provide such a small torque, or then you can have also very large, I don't know, 40, 50 Newton per meter torque that can be provided. Okay, this is typical ranges from few micronewton per meters to tens of Newton meters. Okay, and the output, this is typical for example, machine tools application. The power output ranges, let's say, from few watt, let's say 1 watt, to 3 kilowatt. Okay, so they can be applied for very different kind of application. Okay, typical applications of this kind of motor, let me say, hard disk, head, okay, heads of the hard disk, the driver, printers, numerically controlled machine, photograph application. Some, say, medical devices can be also employed this kind of motor. Application is it's very wide field of application, this kind of motor, having this wide range of torque and power, say, provided by this motor. Typically, stepper motor has no winding on the rotor, okay? So positive feature, if you want, call in this way, positive. No winding are present on the rotor, and this means that we have less maintenance problem. Okay, we have no commutators, no brushes, and so this, say, helps in having motors with very high reliability. Okay, their life can be long. Okay? So this can be a very good feature. So let's just say see a basic stepper motor system. Okay, basic stepper motor system has a block. Let me call this as the controller, or maybe, since we are also call this the driver. Okay, so let's say the electronic part that provides the correct signals for supplying the stepper motors in order to obtain a specific angular position at the output. Typically, this comes with a number of different phases. Let's say that we have just 3 phases, for example. Then we have the motors, and this is the shaft. This is the stepper. So the electromechanical actuator. Here we have the shaft, and the angular position that we call alpha is the output of this rotating shaft. The driver here is our power processing unit, remember from the basic introduction of this course, providing, say, this set of input signal. Okay, this is the number of, say, phases. The driver has a set of control signals. Remember, the set of control signal are, for example, given by, let's say, typical 2 signals are provided. One is the signals that carries a, say, pulse signal. Okay, let me call this as the step pulses. And the other signal that we can call also R is the direction signal. Okay, is a digital, say, signal, B 2 levels signal. Okay, 0 or 1, and this is the direction signal. Okay, every time a pulse occurs on these step pulses, these pulse line here, the motor takes one step at the output. Okay, this elementary step that is related to each pulse provided in this input line here is called the step, and we can call here our alpha step. Okay, this is called the step. The shaft remains in this position, alpha p, until the next step pulse is provided. Okay, then when you have the second step pulse, then you can have another alpha p step. Okay, so as you can see, there is a sort of, say, digital, say, rotation. The rotation is not continuous. The rotation is discrete in its movement. Okay, because you have alpha p, then another alpha p, depending on the pulses you provide at the input. Okay, this is intrinsically is a digital system, if you want to call it numerical system. Direction signal provides the direction of rotation, clockwise or say anti-clockwise direction. For example, you can associate the 0 digital value with the anti-clockwise direction and the 1 level with the clockwise direction, for example. Okay, so it's a system that we can call as, say, intrinsically digital, and then it's open loop. Because if you know that there is a one-to-one relationship between the number of steps that you provide at the input line and the number of discrete position steps that you have at the output, then there is no more need to measure the position of the output. Okay, and then to provide signals that react to this kind of measurements. Okay? There is no need for closed loop position. Okay, so intrinsically this is an open loop. How can we generate these signal here? For example, the step pulses, but you have, say, some. You have several solutions. Of course, you need oscillators, okay, for doing this. And typically, you can use digital controller, microprocessor, or analog solution, like for example, oscillator that are controlled by analog voltage, if you want. Let me just giving some say numbers, some say algebraic manipulation of this discussion. We call alpha p the step of rotation. Then we can say that np, which is 2p over alpha p, is the number of steps that you can have for complete revolution. Okay, for 2p revolution. So this is the number of steps per revolution. Okay, so if you want, alpha p here is 2p divided np. If you have a number of steps per revolution, then you can find the single step alpha p in this way. Suppose that you want, let's say, n is the number of steps that you want to obtain at the output. So this is the total number of steps at step per shaft. This means that you have a total rotation, total position angle, angular position, which is given by the product of alpha p, which is the elementary step, multiplied by n. This is 2p over np multiplied n. Okay, this is the overall rotating angle. Okay, so this is the number of steps. Remember, the number of steps depends, is directly proportional to the number of pulses. Okay, so if you want, this is also the number of input pulses. Okay, so there is this direct relationship between alpha, the overall rotating angle, and the number of input pulses that provides, as I said to you before, the open loop, the position control, etc. When a given number of steps are taken, for example, n, the step pulses are, say, counted, and then we have to wait until the required number of steps is reached, and the pulse train is turned off. Okay, so simply we have to count the number of input pulses, apply this expression here, and then you get the total angular angle at the output shaft. Okay, there is no need to say measure this angle; it can be simply counted. Okay, let's consider a very simple example of this situation. Suppose that we have this is also provided in the slide. Okay, suppose that I have a stepper motor. Suppose that I want to illustrate on a graph which I have time, and then I have the say the shaft angle. Okay, now here I want to provide you say a drawing of the possible input step I can provide to this driver for the motor. Let me just you provide an example with 6 steps, okay, as provided you by the slide. 4, so this is number 1, 2, 3, 4, 5, so and here is 6, the number of the input pulses, so the step pulses. We have this first step here. What happens to the shaft angle? The shaft angle is, let's say, increases. This rotation is alpha p. Okay. The angle is maintained to be fixed until the next pulse coming at the input of the driver. Here you have another step pulse. Then I have another one. And then I have the last one. So here there are 6 step pulses. They are, say, equally spaced in time. So there is a frequency, if you want. This can be also called as, say, the period t. So we have a frequency, which is 1/t of application of this pulse. The motor takes 1 step at a time. Each of these steps are, say, alpha p. And then at the end, we have 6 times. So we have alpha p multiplied n, which is alpha. It's the total angle, as I said to you. First of all, just say discussing some specific feature of this behavior. The total angle alpha here, which is, say, obtained by this sequence, depends on the number n of the pulses provided at the input, which is the average speed of the shaft. The average speed of the shaft can be defined in this way. Let's say omega m which is the average rotating speed of the motor, is alpha divided by what? This time interval is called t. Then we have 1, 2, 3, up to 60. So we can say n divided by t. So this omega, this slope here, is exactly the average rotating speed of our motor. So which is alpha over the time interval here, which is n multiplied by t. Remember that according to our previous discussion, that is reported here from this expression here, alpha over n is 2p over np. Okay, from this one. So this means that alpha over n here can be replaced by the previous expression derived before, divided by t. But 1 over t is called f, so this is 2pf over np, which is the number of steps per a complete revolution. So the average rotating speed of the shafts provided by the output of the motor typically is given by the omega divided np, which omega is the frequency of the pulses. Okay, as intuitively, say something that is very intuitive. Okay, much higher is the frequency of the pulses provided the output, much higher will be the rotating speed of the equivalent average rotating speed of our motor. Okay, so it depends on the frequency of the pulses. The second conditions that we can just discuss in this very elementary example is that the action of the step is not perfect. What does it mean? That I provided you a, say, ideal situation in which after each pulses, immediately the rotation of the speed reaches the correct position. Okay? But what happens that this is not exact, because the rotor takes a finite time to move from one position to the other. And then there are overshoot oscillations. So the typical movement of the rotor is something like this. There is overshoot in position, then there is restoring the position, and so it takes a certain amount of time, okay, which is the common interval of time by which I can have, say, the shaft reaches its correct position. Typically, this is between, say, 5 to 100 milliseconds. And this is the period t that I have here. So from this, you can also understand which is the maximum frequency that I can use for this excitation. Another thing that, if you want to complete my discussion that I illustrated you before, the open loop positioning control feature of this stepper motor, remember, is that we always need a reference position to understand which is the correct, say, final angular position of my motor. Okay, if you have, let's say that if you know that after 6 steps of the input, you have 6 alpha p elementary step, you know what is the, say, the overall angle, but we know the correct position. We don't know the correct position, because in order to know the correct position, we need, let's say, the initial position of the rotor shaft. Okay, so this is something that typically is done in microcontrollers, okay, or something that is related to the driver, that at the end of one action of the shaft, okay, the number of pulses that are provided are stored in order to understand which is the initial position for the next angular rotation. Okay, so in order to give the absolute value of the position, you need to know the initial value of the position of the step. This is something that is quite clear. Let's stay in some random consideration, because we are in a mood of, say, overviewing this stepper motor. So I have to say that the stepper motor are very, how can I say, they are the demand of stepper motor is quite large, because they have an extraordinary ability to operate at very high stepping rates. Typically, in some motor, you can also reach 2000 steps, let's say, per second. And it is very large number, okay, of steps. And even if you are in this very, say, high frequency operation of the stepper motor, they continue to have the good feature of the one-to-one relationship with the input pulses. These say that they do not lose their synchronous with the control pulses, even if they can step at this very large rotating speed. And if you rotate the stepper motor with this large number of steps per second, then even though the system is intrinsically digital, I said before, the rotation seems to be continuous. Okay, there is no, say, discrete effect as the operation I indicated before seems to, say, to provide. Okay, when the motor is operating in this high-speed operation mode, is called the slewing mode. Slewing mode is the typical operation of stepper motor. Very large number of steps per second. The rotor, say, rotates in a way that it seems a continuous rotation between, say, understanding or, say, understanding the fact that under this continuous rotation there is a step fashion, a discrete movement, and this is typically the standard way to operate this stepper. Okay, but together with this good feature, there is another, say, very important characteristic of stepper motor, that even though they can, say, rotate in slewing mode with this large number of steps per second, they stepper rotating frequency can be, say, increased or decreased in a, say, fast way. Okay, they can be reduced or, say, increase the number of stepper in, we say, very quickly with respect to other kind of motor. So the inertia of the motor depends on the construction, but typically can be, say, very low. We have to pay attention, because if you are in a slewing mode, so stepping rate is very high, and you want to, for example, suddenly stop the motors, okay, then in that specific case, the synchronous I, say, described it before between the rotating steps and the total number of pulses provided at the input, that in this case is lost. Okay, there is no more synchronous. So when you are in the slewing mode, if you want to, say, stop your motor, for example, you have to do this, say, by slowing your command pulses up to the point you, say, go to the rest position. The same happens when you are, say, in the situation where the motor is stopped, no rotation, and then you suddenly want to go into the slewing mode. This is not possible. There is no more synchronous between the number of steps and the number of pulses you provide at the input, and then in that situation the motor will stall, sometimes lose synchronous, and also stops. Okay, no more movement. So also in this case, you have to increase the number of pulses slowly up to the point you are operating your stepper motor in the slewing range. So this is just for, say, giving you a very generic and elementary overview. Next, I want to describe the different variety of stepper motors construction. Okay, and in doing this, some of these characteristics, the origin of these characteristics I just explained and mentioned here will be a little bit more clear. Okay, so let's start with the topic, which is the, say, let's call this type of stepper motor. There are three different categories of stepper motor. The first one is called the variable reluctance stepper. Then we have the permanent magnet stepper motors. And then we have the so-called hybrid steppers. Okay, variable reluctance stepper motors. In this case, we have winding on the stator rotor, which is made by ferromagnetic material, without any coils. Okay, so the only windings are placed on the stator, but not on the rotor, as I also mentioned at the beginning of this class. Another characteristic, these are construction characteristic that is an operating characteristic, is that the direction of say motor rotation is independent from the direction of the current flowing to the stator winding. This is the general class, these stepper motors. Just to mention the most popular, we can have the single stack variable reluctance motor or the multi-stack. Let me call VR for variable reluctance, okay? Permanent magnet stepper motors. Again, we have winding only on the stator. No winding, no coils on the rotor, but the rotor is made by permanent magnets. Okay, and this is the difference with respect to the variable reluctance motor. In this case, since we have permanent magnets, the rotor is cylindrical. The section of the rotor is cylindrical. We can see in a few moments that the shape of the rotor for variable reluctance motor is not cylindrical. They have, say, some expansion, some pulls. Now, the motor direction depends on the polarity of stator current. Okay, this is different from what happened in the variable reluctance motor. The third and the last characteristic, the last kind of motor is the hybrid stepper motor. In this case, it combines both variable reluctance motor and permanent magnet motors. Let me call this PM and this is VR. Okay. The winding are again only on the stator. The rotor is made by permanent magnets, and you can see later that this kind of construction try to combine the good feature of variable reluctance and permanent magnet. Okay. So let's start discussing the behavior of variable reluctance motor. Okay. In order to do that, let me just share the slide. Here. Okay, so this is the slide showing you a very basic example here, okay, of the principle of motor operation for a variable reluctance motor. By the way, this is also true, this discussion, for hybrid stepper motor. Okay, so take into account that what I'm saying here for variable is reluctance motor can be also, say, the discussion of the principle of hybrid stepper motor. Okay, the principle is the principle of operation is very simple. When a bar of iron, say steel, is say free to move, free to rotate in a magnetic field, it will align itself with the field. Okay. This is done in order to make the complete magnetic circuit which is involved having the less reluctance possible. Okay, the reluctance is one of the most important parameters of magnetic circuit. Okay, but anyway, if you have a bar which is free to move, to rotate, this bar always align with the direction of the magnetic field. Okay, suppose that you have this bar in a space, in a region of space in which there is a magnetic field, and this magnetic field has a specific direction, then if the bar is free to move, to rotate, then it will be aligned to the direction of the magnetic field. Okay, if the direction of the field changes, the bar will turn itself until it is again aligned. Okay, what is the kind of force that make possible this? As I mentioned before, is due to the fact that I need to minimize the reluctance of the magnetic circuits. And specifically, the action is the so-called reluctance torque. Okay. Just to say, spend a few words about these reluctance torques. In the lectures that I given for the students in electronics, I talked about this reluctance. But anyway, in standard, say, motors, typically the torque which is generated by the rotating machine is always produced by the interaction of a magnetic field, which is produced by stator or rotor, okay, with conductors that carries current. In that specific situation I'm showing you, there is no such way of interaction. Okay, because we have a magnetic field, and the magnetic field is generated by the current flowing into the stator winding. But on the rotor, there are no conductors carrying a current. Okay, so here the way to generate the torque is not the standard way you can find in non-reluctance motors, like for example the DC motors or the AC motors. Okay, In that kind of motors, there is no reluctance torque. There is only this kind of torque generated by the interaction of magnetic field and conductors carrying a current. Okay? Here the situation is totally different. Here is exploited just the reluctance torque. Okay? And in order to exploiting this reluctance torque, the rotor, which has no winding on them, no current carrying conductors, needs to be shaped in specific form in order to enhance this reluctance torque. Okay? And this means that the shape of the rotor has some expansions, has different teeth, poles, call as you want, but they have to be shaped in order to, say, have a varied reluctance according to the rotation of the rotor. Okay. While, for example, DC motor, AC motor, which does not exploit this reluctance torque, has a shape of the rotor which is always cylindrical. Okay. So let me just discuss the operation for this very simple variable reluctance or also hybrid stepper motor. Okay, the discussion here is made for a stepper motor that has, this is the cross section. Okay, the cross section has, as you can see here, six poles on the stator. 1, 2, 3, 4, 5, 6, and then you have a rotor that has 4 teeth or 4 poles, okay, 90-degree apart. The rotor is free to move, so there is an axis entering the plane of the slide here, and the rotor so can rotate clockwise or anti-clockwise around this axis. Let me just discuss a little bit about the winding on the stator. Okay, the winding you can see here, for example, puts your eyes on the A section here, so the vertical one. You have winding. This winding is connected to this expansion, this pole here, and also to the opposite one. They are connected in series. Okay, they are the same winding. The current flowing here, okay, goes also here and exit here, enters here, for example, and exit here, or the opposite also true. So the two windings that you can have on each of these opposite side of the stator expansion are always in series. They carry the same current. Okay, so as you can see here, we have AA, which is the phase A. The expansion B is the phase B, and C is the phase. So we have a system which is a three-phase system. Okay, there are 3 coils, three windings. Okay, and these 3 windings carry a different current. Okay, this system is also represented here in terms of an equivalent electrical system. Okay, we have the phase A, which is represented as the equivalent inductance and equivalent series resistance of the coil. And then we have a switch SA, SB, and C that commands the flowing of the current in each specific phase. Okay, this is just an electrical view of what happens here. Okay, so let's start with the condition which is illustrated in the left end of this slide. Okay, we have current flowing in the phase A. This current and no current flows to B and C. So in this circuit that you can see here, it's like you have SA, which is closed, SB and C that are open. Okay, just the switch A is closed. So the magnetic field which is generated by the current flow into the winding A has a specific direction, and the direction of this magnetic field for this construction is vertical directed. Okay, so the current in the stator phase A generate a current, a magnetic field, which is vertically directed. What happens? It happens that in order to reduce the reluctance of the magnetic circuits, the rotor aligns itself in the position of the minimum reluctance, okay, which is the position in which the arrow, the white arrow on the rotor, is vertically placed. is aligned in the direction of the magnetic field. Takes also note that if the current, this position is obtained independently of the direction of the current, because even if the current is entering here and exiting here, or entering on the bottom and exiting on A, so that direction is reversed, the direction of the magnetic field is always vertical. And so the bar here of the rotor always aligns itself in this vertical position. So the position is not dependent on the direction of the current. Now, what happens if we move the excitation from the phase A to the phase B? According to these electrical equivalent circuits, SA will be open, SB will be closed, and C will remain open. Okay. In that situation, the current flow in this direction. Let's see that now we are moving to the middle circuits, middle cross section here. The current is here. Okay. Now the current provided by this winding excite a magnetic field which has the direction which is axial to the B phase here. And so it means that this pole, which is indicated here, rotates clockwise directed in order to minimize the reluctance, so to align itself with the direction of this magnetic field. The total angular position that I get here, the alpha step, is 30 degrees. Okay, so this is exactly the alpha p, the elementary step provided by this elementary motor here. Then suppose that I move excitation from the B phase to the C phase, so SA open, SB open, SC closed, and then is the situation depicted in the right part of this, say, cross-section side. Okay, here the current is flowing this winding. So what happens that the magnetic field is oriented exactly axially to this C phase, and this, say, expansion here, okay, by the reluctance torque is accelerated up to the point in which it is aligned with the direction of the magnetic field. Again, we have another alpha step of 30 degrees, and the overall angle is now 60 degrees. So we have A, B, C. Now it turns to be again the A turn. Okay, so we are now exciting again A. The situation comes to another, say, static position, equilibrium position, which this point here is aligned itself, okay, with this guy. So let me see that if this solution when we have A, B, C, A, etc., provides, let's say, clockwise rotation of this rotor. If you consider the possibility to exchange the order of excitation from A, B, C, A to A, C, B, A, now what happens is that the rotation is counterclockwise, is anti-clockwise. Okay, so in order to rotate the rotor in one direction or the opposite direction, it simply means of, let's say, this correct sequence of excitation of the different phase. Okay. The behavior I illustrated to you before is summarized in the table you can see here, which you can say the phases A, B, C, the total theta, which is the total angular position. I call this alpha. Okay, is the angle which is measured from the vertical position, clockwise directed. 0 means that you have no excitation. Okay, and plus means that you can have the phase is excited. Okay, and so we get this table. This kind of operating mode is called one phase on, because the phases are excited one at a time. Okay, we have the ABCA rotation, so it's clockwise direction. ACBA is the anti-clockwise direction. Okay, so in the previous description, I see that the alpha step is 30 degree. Okay, there is the possibility to say evaluate the alpha step. Okay, simply by taking into account the number of phases you have and a number of teeth of the rotor. Okay, this expression that you can see here provided you exactly this number of steps that you can have depending on m, which is the number of phases, and on r, which is the nr, which is the number of rotor teeth. Okay, the number of steps for complete revolution is exactly the product of the number of phases and the number of teeth of the rotor. In our case, we have 3 phases and we have 4 rotor teeth. You have, let's say, 12 steps for a complete revolution. And since a complete revolution is 360 degrees, it means that we have 30 degrees as alpha step. Okay, so take into account that this is the correct way to evaluate the number of steps for revolution or the alpha step. If you want, it should be also clear from this equation that if you want to get very small angle, very small alpha p, you have to increase m or you have to increase nr. Okay. M means that you have to increase the number of phases, so you have to have more windings. Okay. And NR means that you have to increase the number of rotor teeth. For example, let's say that if you want, for example, choose 200 steps for revolution, okay, you can have 4 phases and 200 rotor teeth. You can see that just for this simple number, this is something that can be done. Okay, but if you want to get very small angle step, much lower than 200 steps for revolution, for example, there is mechanical, let's say, difficulties in increasing the number of rotor teeth, for example. And typically more than 4 phases is something that cannot be accepted because the number of windings is say, increasing. So there are some physical limitations that typically does not allow to increase the number of the total step of revolution to be a very large number. Okay, typically for variable stepper motors that are exactly manufactured in the way I show you, the angle is not very, it's very small. Typical angle ranges from say 15, maybe 7.5 degrees, 30 degrees, 45 degrees. Okay. We'll see later that the hybrid solution can put this limit to 1.8 degrees, 2.5 degrees. Okay, we can have much number of step per revolution, so the resolution can be finer in that case. Okay, let me just to this is a sort of qualitative way of description of this principle of operation mode. There is another way to describe the same operation mode, which is based on the static torque displacement curve. So let me just stop this sharing and share my whiteboard. And in order to see what is this static torque displacement curve. Suppose that we have the same arrangement I described you before as an example. Okay, so the variable reluctance torque, which is made by 3 phases A, B, C, and a rotor, which is made by 4 rotor teeth, okay, spaced by 90 degrees. I want to put on a graph the following variables. Okay, here I have the angle, let's say the displacement angle. And on the vertical axis, the anti-clockwise torque. Let me just put here the cross section. Okay, my drawing is, say, something which would be horrible, but you saw before the correct drawing, so with a little bit of fantasy. Okay, this is the stator. So we have A, then we have B, we have C phase, and we have the rotor. Let me put in red. Which rotates on this axis, vertical axis. Okay, so this is the same cross section I described you before. Okay, what is the anti-clockwise direction? So before we have to define what is the displacement angle. The displacement angle is the clockwise angle. Let's say starting from here, 0. Okay, so this is the displacement angle. Basically, the situation is the following. The anti-clockwise torque is exactly the torque which is developed by this arrangement, this magnetic arrangement, that tries to restore a stable position of the rotor. Suppose, for example, in order to understand what I'm describing, that this is a stable position. Okay, supposing that I'm exciting the A phase, B, C are not excited. As you can see here, the alignment is, let's put here imaginary, say, arrow here. The position is stable, okay, because this arrangement provides the minimum reluctance torque. Okay, so the system has no, say, reason to move from this stable position. Okay, in this condition, there is the alignment between the rotor and the magnetic field direction generated by the stator current. So this is a totally static and stable position. But suppose that now I displace the position of the rotor. For example, I put, say, I change the position a little bit. Let's say in this way. Okay, I manually, for example, I force the rotor to have this displacement angle here. Okay, so suppose that I have this positive angle according to this graph here. There is what is called the restoring reluctance torque. The restoring reluctance torque is a anti-clockwise torque that is applied to this rotor in that position that will restore the static position that I had previously. So it is a say, anti-clockwise torque that restore the red static equilibrium position. Okay? So this graph here is exactly the plot of the anti-clockwise torque generated by each phases when you have a clockwise displacement of the rotor. Of course, when you are in no displacement, this anti-clockwise torque is null. Then this has this kind of plot. This is for the phase A, okay? For example, if I have this angle of displacement, okay, suppose that this is theta prime, okay? Suppose this theta prime is here. I see on the graph that the magnetic circuits provide you this anti-clockwise torque. This anti-clockwise torque is responsible for providing a, say, movement of the rotor that ends with the original position. Okay, so if I move the rotor, then the displacement torque, let's say, move the rotor anti-clockwise in order to restore the perfect position. Okay, as you can see here, this torque, which is developed by the phase A, has a maximum here. The maximum here is at 30 degrees. So if you have 30-degree displacement, and 30-degree is more or less is the position I provided you before here, say, which is in between of these two, okay, because this angle here is 6 degrees. In this case, the anti-clockwise torque is exactly the maximum. This position, which is 0 or also 90 degrees position, are called stable position. Because they are called stable. Because if you change the position from 0, for example, a little bit, as I said before, providing you theta prime, then the restoring torque, the anti-clockwise torque, always provides the magnitude of the torque that shifts the rotor in the correct position. The same happens here. These other points, 45 degree and etc., are unstable position. Okay, because if you are here, 45 degree, which is something, let's say here, for example, if you have the rotor in this position here, in that case, if you get a small displacement for this position, for example, you got here, instead of having an anti-clockwise direction that restores the correct position, the direction here is the torque is negative. So it means that here you have a clockwise torque. Okay, so the torque here accelerates the rotation in the clockwise direction until a next stable position is provided. I hope that this discussion is enough clear. If it's not enough clear, ask me, okay? Of course, yes, I have a chat. The definition of the anti-clockwise torque, sure. Do you understand that there is certain situations, certain position of the rotor that are stable? Stable means that the rotor does not move from that situation. For example, when I excite phase A in this way, the stable position is that, let's clean up this. The stable position is exactly this way. Okay, let me put this way. Okay, this is the stable position. What happens if I move a little bit from this stable position the rotor? For example, let's put this rotor in this other position. Let me go this way. I change a little bit the position in the clockwise, so I'm moving in this direction, which is clockwise. So if I now displace the rotor for this, let's say, angle, theta prime here, okay, and I left free to move the rotor, this rotor naturally goes into the stable position. And why it goes into the stable position? Because there is what is called a restoring reluctance torque. Is the torque generated by the current flowing this winding and by the rotor that naturally is in the direction to move the rotor in the anti-clockwise direction, restoring the correct natural position. So the anti-clockwise torque is exactly the torque that provides, after a displacement of the torque, the restoring of the correct stable position. Okay, in this way, in this kind of graph in which I have a displacement angle that are clockwise direction, the torque is anti-clockwise for restoring the correct position. Okay, if I move clockwise the position of the rotor, then the torque will act in anti-clockwise direction to restore the correct position. Okay. Antonio Moles is okay, is something that's okay. So this happens, so the stable points are here and 90 degrees here, so exactly the position which is 90 degrees apart from this, but there are also, say, in between unstable positions that are 45 degrees displaced. So this is happens just for exciting phase A, but I said before that I have to excite for clockwise direction, rotation A, B, and C. Okay, so let me just put on the same graph also the graph for the phase B. The phase B is something which is something like this, phase B. Okay. Do you have another question? When we are in 30 degree and C is in conduction, okay, now I'm going to say put the other phase on. Okay, now the discussion here is just for the A excitation. We'll see in a moment what happens when I change the phase rotation. Okay. Another question. So the restoring reluctance or move the rotor to the minimum reluctance so is in a stable position. Exactly. Exactly, Antonio Moles. This definitions you want to say is exactly what I'm saying. So the B phase is excited after the A phase. Okay, so now we have B position here and B position here. When we are in 30 degree, and 30 degree is the position that I have, let's say, here. This is 30 degree. What happens that the position is stable for the phase B. Okay, so without the excitation of the phase B, we are at the maximum point for the phase A. So if I not excite the phase B, the anticlockwise torque will restore the position 0 for the phase A. But at this point, I excite the phase B, so the system will go in a stable position for the phase B. So it remains at 30 degrees. Okay, so the step is completed because instead of having here a restoring, say, position toward the position 0, the system will be stable in this position here. And the same discussion can be done for the phase B, which now is the only excited phase. Then we have the phase C excited. Okay, and when we have the phase C excited, it means that you have another curve like this. And so when we reach the maximum possible torque for the phase B, restoring stable position for the phase B, we excite phase C. In that case, the position will be stable for, say, the position of the phase. So if you want, a more, say, qualitative discussion of the way this motor, say, finds stable position step by step is due to the consideration of this anti-clockwise torque acting on each stable position of the system. Okay, so we have phases that are excited, say, one after the other, just to, say, acquiring for the rotor successive, moving the rotor in successive stable position for the phase that I'm exciting. Have you questions about this discussion here? I want to describe this mechanism just by illustrating this graph, because it would be able to understand some other, say, operating mode of the stepper motor without using mathematical, also because this is not the case. I want to go, say, very fast to this part because I want to, say, discuss the electronics driving the things, okay? But if you have questions, of course, I'm here to understand this point. Problems, issues? These curves are excited just one at a time, not simultaneously at this point, okay? We are discussing what is called the one phase on system. Remember, one phase on means that just one phase is excited at single moment. Okay, if you have no question, you can think about in the break. Maybe you can ask me later the break. We can have a 10 minutes break from now, so 52, let's say, up to 1 and 3 minutes, okay? Before continuing, I have two questions. One for Emanuele Elia, that we are in a high frequency rotation. We cannot vary the step frequency to low values. It is also valid vice versa. Yes, I also mentioned about this fact, Elia. If you are in, say, for example, your motor is stopped, okay, and you immediately suddenly accelerate the motor to get into the what is called the slewing operating region, that the motor goes into the what is called the stall. It blocks. Okay, there is no more relationship between the step you can get at the rotor and the number of pulses you provide at the input. It's called the stall of the motor. It is basically, it does not move anymore. Then you have to lower your number of pulses, and then the motor, say, reget the correct rotation speed. Antonio Moles, can I excite two seats concurrent? Exactly. This is something that we can say explain later. Okay. Just for now, remember I describing what is called the one phase on. The one phase on means that they have just one phase activated at a moment. Okay. But later we can understand that there are also the possibility to have, say, more phases activated simultaneously. Okay, just to continue what I'm saying, but with the slide. Okay, here in the slides you see the much better drawing of these clockwise and counterclockwise torque versus the angle. Some basic consideration hypothesis that I said, but is worthwhile to repeat. The first one is that I'm just considering the one phase on excited. Okay, so A, then B, then C, etc. Second one, and then I'm considering that the current flow into the phases A, B, and C is the same among them. Okay, if you get, say, 1 amp, the maximum value of this current, 1 amp for phase A, B, and C. Okay, there are no difference in the current flow into the different phases. Okay, so according to my, let's say, description of this anti-clockwise torque, now the same description that I had before in terms of alignment of the rotor in the direction of magnetic field to reduce the reluctance torque can be also described in terms of this graph here. Okay, suppose, for example, that we are in the left hand position that you can see on the top of this slide here. Okay, and so we have the phase A, which is excited. The phase A is the continuous line in this graph A, and we are in the angle 0 degree. Okay, so we are in a stable position. Then we excite phase B. Okay, and if we excite phase B, you have to look at the middle graph here, middle cross section, which we have the phase B excited. And now the curve that I have to look at is the dashed line, which is the phase B clockwise, anti-clockwise torque. Okay, because A is no more activated. You are in the 0 position, the phase B is excited, which is your clockwise, your torque is negative, is here. Is that due to the phase B? What does it mean, negative torque? The torque is clockwise. Okay, is anti-clockwise. If positive is negative, means clockwise. Clockwise means that the torque which is developed by exciting phase B is in direction of moving the rotor clockwise direction up to the next stable point, which is here. So the rotor moves by 30 degrees. When you are here and then you excite the dot dashed C line, okay, the phase C, again, the rotor experiences a negative torque, so clockwise torque, providing rotation up to the next stable point, which is 60 degrees, etc., etc., etc. Okay? So in the same explanation I gave you before, just say very qualitative, now is a little bit, say, detailed in terms of the torque developed by the motor, like for each phase which is activated. Okay, so this explanation is made by do not take into account the load, mechanical load that can be connected to the rotor shaft. Okay, so this is the no load description. What happens if you have a load? Suppose that you have a load and this load provides a torque which is, for example, a clockwise torque TL, which is the stable point, the static, the equilibrium point in this case. The equilibrium point in this case will be the angle, say, of the rotor at which an anti-clockwise torque provided by the motor is exactly the same of the clockwise torque provided by the load. The intersection point of these two curves provide you the stable angle. Okay, so again, this is the phase A which is excited. Positive torque provided by the motor means anti-clockwise torque. Negative torque provided by the motor is the clockwise torque. The opposite sign convention happens for the load. Positive load means clockwise torque. Okay, so the torque TL here is the load torque which is clockwise. The equilibrium point is at the intersection between the anti-clockwise torque provided by the motor and the clockwise torque provided by the connected load, TL. Okay, so TL is the torque clockwise provided by the load. The intersection provides you an angle. But look, the angle is no more 0. So the equilibrium position when you have a load connected to your load, your shaft, okay, means that you have an error in the angle position. Okay, you want to say have a equilibrium position at 0, okay, exactly vertical in that previous example, but now we have error, which is theta E. Okay, let me share the whiteboard here to further insight into this mechanism. So this is the phase A, which is activated, let's say here, for example. So this is the anti-clockwise torque of the motor, and this is the clockwise angle, displacement angle. Okay, this is my clockwise load torque. Okay, now I have this error here. So the equilibrium point is here, is no more, say, at 0. It's the same of having, let's say, my rotor this is the stator, okay, and I have the rotor which is in a position which is stable, that has this theta E angle. Okay, this is the rest position of my rotor. Okay, then of course if you change it from A to B, the other equilibrium position will be not exactly at let's say 30 degrees, but will be something which is, say, slightly different from this position. Okay, this error here is one of the most important drawback in the stepper motor. What you have to be done in order to say reduce this error to a minimum value, what is typically done is to use motor that has this anti-clockwise torque generated by the motor as steep as it's possible. Okay, for example, if I have a car which is generated by the motor, which is this one, okay, then my error will be much smaller. Okay, but typically when you have a torque that has this steep variation, okay, that also has a larger torque generated by the peak is higher, you can say in this way. Okay, and which is the meaning of this peak. But what happens, for example, if my load torque is let me draw here the graph. What happens if my load torque is, for example, here? If the load torque is higher than the maximum torque developed by the motor, then we get no rest position for our rotate, our rotor. Okay, so this is the reason why this maximum torque is also called the max, and is called the holding torque. Is the maximum torque developed by the motor by which we have rest position for my rotor. Okay, if you want to get smaller error, you need a specific motor having higher holding torque, and this means that you are using a motor which is overestimated for your application. Maybe your holding torque you need is a smaller one, but you need to buy a motor with a higher holding torque just to reduce the error, the static error. Okay, so this is something that is not say very this is a drawback of my motor. Okay, just buying a bigger motor with higher holding torque just to reduce the error. Let me just continue this description by illustrating another important point, which is somewhat anticipated by one of you before in the question. Here I'm just illustrating the one phase on, meaning that one phase is excited at a time. Okay, what happens if I'm exciting two phases at one time? Okay, for example, what happens if I excite simultaneously the phase A and the phase B? So I make the switch in the previous description. Remember the switch here. Both SA and SB closed, SC open. If I use this condition, this is called the two-phase on situation. Let's see what happened in my torque graph generated by the motor. I have the curve, let's say A, and I have the curve for the torque generated by B, something like that. Okay, these are the two torque generated by the motor. This is the angle. If I excite simultaneously A and B, I get the summation of these two curves. Okay, so it's something that starts from here, that has a value which is something like here. This A plus B developed torque. We get a rest position, this is the stable position for the new torque, which is in between 0 and 30 degrees. And specifically, if the two currents A and B providing the torque for the phase A and B are the same, this point is 15 degrees. So my rotor now gets a rest position which is exactly in between the steps. Okay, my rest position is here. What is the advantage of having this solution? Basically, I do not increase the resolution because my motor always has an alpha P which is 30 degrees. Alpha P is the same as before. In my previous example is 30 degrees as before. Now, rest position of the shaft is at 15 and then degree, then 45 degree, then 75 degree, and 105 degree. Instead of previous was 0 and then 30 degree, 60 degree, 90 degree. Okay. So I just moved in between, say, my rest position. But look at the graph. I have the same current as before for each phases. But now the total curve has a steep variation and has a higher holding torque. The steep variation means that here the slope is higher than this one. And so it helps to reduce the static error. And in application, if you maybe needs a higher holding torque with a motor that the holding torque for the phase one on is, let's say, not so high for your application, then you can use the two phase on just to increase your holding torque, because the holding torque is increasing. Holding torque increases. Theta E error in position decreases. Okay, so just exciting two, say, phases simultaneously, that we get benefits. Okay, we have to say that there is also a drawback. In the previous situation, I have just one phase on, so I have a current flowing in just one phase. Now we have the same current flowing in two phases. So if you want the power, the electrical power dissipated is, say, twice the power I had before. Okay, so as a drawback, power dissipated is twice. Okay, so this is the drawback, and then is the situation for the benefit. Okay, Antonio Moles, I answer your question. Okay, just share this slide here, because this slide exactly show in a much better way what I'm, say, drawing in the whiteboard. Okay, here is the table of the two-phase on mode. You can see that now the phase C is, say, in the first step is not excited, A and B as excited. Then if you want to move into the clockwise direction, A is not excited, B and C are excited. Then A is C, and then we'll start with A and B. The sequence for counterclockwise is AB, BC, CA, and B. If you modify this direction, this sequence, then you can get also the anti-clockwise rotation. What happened? Okay. Half stepping. Suppose that my resolution in terms of alpha step, my alpha p, the elementary step provided by the motor shaft, is not enough. Okay? There is a way to use the same motor but with a different excitation that make possible to, let's say, make this alpha p exactly half the value you have in our previous consideration, our previous case. Our previous case was an example with the 3-phase and 4 rotor feet, giving us alpha p of 30 degrees. Okay, but with the half stepping, we can get alpha p of 15 degrees. This sequence of operation is alternating the 1-phase on and the 2-phase on. Okay, suppose that you have this situation. Okay, look at what happens in this table. I start with my phase, which is let's say A is excited. Okay, so B and C are not excited, so we are stable in position, say 0 degree. Then at the next step, I go into the 2-phase on, so I'm exciting A and B. In that situation, I'm alternating the 1-phase on, just A excited, with the 2-phase on, A and B simultaneously excited. And this means that I can get a stable position which is in between 0 and 30 degrees, basically 15 degrees. So I move to a stable position which is in between. Then I get just B phase, so I got 30, B, C, 45, etc. So alternating 1-phase on and 2-phase on, it happens that you can make your alpha p exactly alpha p divided by 2. Okay, you are halving your alpha p from 30 degrees. Now you can get 15 degrees. Okay, so this is what happens for is a way to make possible this kind of half stepping mode. Okay, so we get the 1-phase on and the 2-phase on. Basically, they have the same alpha p. They're different performance in terms of the torque and in the error position. And then you can have the half stepping. The half stepping is the alternating way of a 1-phase and 2-phase on, making the alpha p half the value you have before. Okay. There is another say employed technique to further reduce your alpha p to very small value. Okay, remember what I said previously. Remember that equation that provides the alpha p value as a function of the number of rotor teeth and the number of phases of the stage. Okay, as I said, okay, you can increase the rotor teeth, you can increase the phase, but pay attention that if you, for example, get more than 4 phases and more than 200 rotor teeth, it's very difficult to, simply by construction, a rotor having a large number of rotor teeth. So there is maybe physical and constructive limits to the number of rotor teeth, the number of phases that you can add. But there is another way to have, say, reducing this step. Okay, let me share the whiteboard just to illustrate the technique, which is based on the, again, to the torque. Okay, look at this graph here. In this graph, you have the two-phase on. Okay, this is the two-phase on of the stepper mode. If you look at these two-phase on, I have the same current flowing to the phase A and the same another current which is the same, equal to that of the phase A, which is flow in the phase B. Okay, so we have two curves, the red one and the blue one, that are basically the same in terms of provided torque. Okay, they have the same peak, they have the same extension, etc. The summation is the yellow one. But what about the situation in which I change the current exciting one of the two phases? Okay, for example, what happens if I have the phase B is not excited with the same current level of the phase A? So let me consider this fact. I have the phase A, for example, this one, and then consider the phase B, which is the phase B obtained by the same current I use for the phase A. Okay, now the point at which I have the say the equilibrium point is the point providing by the summation of the two. Okay, if I get the summation of the two, I have something which is here. Okay, this quantity here is positive. You have the same quantity here, which is negative. Okay, the summation of the two provides here 0. Okay, so the summation of the two pass through 0 here. Okay, and this is the stable point. Now, suppose that my B phase is excited with a current which is not the same of the phase A. So this changes completely the curve of the developed torque. For example, I can have something which is, let's say, okay, B prime, and so B prime is obtained by a current through phase B different from that flowing through phase A. Okay, so I have the red curve and then I have the dashed curve. Now, my stable point is stable angle is at that specific point which the summation is null. Okay, so for example, it can is here, stable point. So simply having different value of the current here, I can modulate the point at which the summation of the torque developed by the two simultaneously excited phase A and B is 0. Okay, this is the basic principle under which stepper motors provide mini stepping. In mini-stepping operating mode, currents in phases are, say, fine-tuned to precise control rest position. Okay, so I can change this, say, quantity here with the very fine tuning steps for the current, and I can modulate a stable point for very, say, minimum interval of angle. Okay, during this kind of operating mode, you can also, let's say, reach angle that are 0.18 degrees. Okay, so this means if I compute correctly, 20,000 steps for revolution. Okay, so this means that you have very precise control. Of course, what is the drawback of having this kind of characteristic? That the current should be provided in a very accurate way. Okay, because changing the current, the torque provided by the motor is a very sensitive function of the current you are, say, putting in your winding. Okay, and if you have so fine tuning, it means that you have to pay attention to, for example, the variation of the temperature. Because if you vary the temperatures or others, say, environmental conditions, this current can be changed a little bit. Okay, and so this means that you can have error in your position. So that means that typically mini-stepping stepper motors are including always a closed feedback system that measure now the position accurately in order to avoid this kind of problem. Okay, the position provides, say, the measure of the position provides you information about what kind of current I have to use for each phase in order to, say, provide correct operation. So what I do not need typically for large stepper motors for large, say, resolution, alpha P larger than, say, a few degrees, in mini stepping now is something that is needed, the closed loop control. Anyway, some applications, say, are say, based on this kind of mini stepping. For example, say, photographic application, okay, for photo camera applications. Printing application when you need very high resolution. Say this typical solution is always implemented. Okay, so my explanation here is based on the static torque curve displacement. Okay, let me share the slides. Remember what I said at the beginning, the stepper motors can be single stack or multi-stack, just say. Okay. Just to see what is the difference, they know that you to have a more knowledge about the stepper motors, this overview. All the operating principle I described up to now refers to any kind of variable reluctance mode. Okay, the construction that I show you is the construction for the single stack. Okay, so the same description of the operation principle always is true for this another kind of variable reluctance mode, which now is called multi-stack. So in that situation, we have that, look at this. Now the cross section here is not the transversal, is the transversal cross section. It's not the cross section I showed you before. Now the motor is, say, cutted, say, in this direction. Okay, not in the axial rotational direction. This axial rotation is here. Here you can see there is a stator. Okay, and the stator, for example, in this example, has three expansion. Okay. This, of course, the stator, this part is fixed, cannot move. What is moved is the rotor, which is now composed by 3 stacks. Okay, A, B, and 3 stacks. They are isolated, but they are connected to the same rotor shaft. Okay. Here you can see a picture in which you can see, say, the same, basically the same structure. Okay. Here you have 4 stacks, not just 3. The 4 green part here is just 4 stacks. But anyway, what happens? That the stack rotor are, say, basically the same. So they have the same number of teeth. And the stator have their expansion, but they are not, let's say, aligned. For example, the poles, the stator expansion that you can have here in the part A are not aligned that you can have in the phase B, or that you can have in the phase C. There are a slight, say, separation. So this is the development graph, okay, of this structure here. You have the rotor, they are the same, they have the same, say, number of teeth, they are aligned, the teeth are all aligned in the stacks, while you have this different behavior for the stator. Okay, the stator A has this expansion, the stator B has the same extension, but say there is an offset in the position. For example, these and these are not, say, positioned, they are not aligned. The stack C are the same, say, disalignment of the stacks. So that means that when I excite A, okay, for the variable reluctance, there is alignment between the rotor sticks and the expansion of the stack A. When I excite B and not A, for example, I have the alignment of the rotor with the poles of the stack B. And then with this rotor, the rotor will be aligned when phase C is excited with the expansion of the stack C. Okay. But as you can see here, this means to increase the number of stator phases, stator expansion, without mechanical problems, because I use 3 concentric stator expansion structures, and this can be employed to provide a finer resolution for the stator, for the stepper motor. Okay, the resolution is provided by 2p, okay, is indicated in this equation, divided by the number of rotor teeth. For example, in this example, you have 20 rotor teeth, and the number of stack. In this example, indicated here, you have 6 stack. 6 stack and 20 rotor teeth, you can have 3 degrees. Okay, so you can enlarge the resolution. You have a very less resolution, but basically the operation is the same. Okay, single stack or multi-stack, you can have the same behavior. Second kind of stepper motor is the permanent magnet motor, which is the difference. The difference is that while in the variable reluctance you are exploiting exactly the reluctance torque, and the reluctance torque always require a specific, let's say, arrangement of the rotor. Okay, the rotor is no more cylindrical. The rotor is, say, as teeth expansions, because we have to exploit the variation of the reluctance according to the excitation of the phase. Okay, but we can get similar behavior by removing the rotor, the ferromagnetic rotor with the teeth, and replacing with a rotor which is now cylindrical, but having a permanent magnet, providing you so a north and a south pole, or more than one north and south pole. For example, this picture here shows you that now the rotor is cylindrical, you can see here, but it's made by permanent magnets that are embedded in this rotor. Okay, this permanent magnet here provides a north and south pole. So the explanation is quite similar to that I show you for the variable reluctance mode. So you can obtain basically the same behavior, but now the I can say the operating principle is totally different, because now is due to the fact that exciting different phases, we are generating a north and south pole, and this north and south pole attracts or not attracts the poles in the rotor due to the embedded magnetic permanent magnets. Let me just discuss a little bit with the whiteboard. A fact that I hope that this is something that you already knows. Suppose that you have, say, a material which will be, say, a magnetic core, and then you have a wire which is wounded in this on this core, okay? Something like this, okay? I have a current flowing here. When a current is entering a node, let me call this current I plus, okay? The current is flowing here in that direction. Remember the right hand rule. That means that if you, say, wrap your right hand across this material, across this magnetic core, and you look at the direction of the current, okay, then your thumb, which is here, indicates the position of the north pole, okay? So here you have the north, and then you have the south. So when you have a magnetic core and then you have a current flowing to this, according to the right hand rules, you can have, say, a generation of a magnetic field having a south in one, say, ends, and the north in the other ends, okay? If you follow this principle for the wire that you are winding on the stator of your stepper motors, then this is responsible for the attraction, or say the repulsion, of the north and south pole of the permanent magnet in the rotor. And this is the principle of the operation. Let me show you the slide here. The example here is for permanent magnet, very simple permanent magnet. Now you have just two phases. Previous example for variable reluctance was three phases. Now due A and B. And then suppose that you have a permanent magnet rotor having just two poles, north and south. Okay. What happens? Suppose that we start with the position A. Okay. Let's excite the phase A, okay, and not the phase B. So again, one phase on principle. Okay, I have the current flowing here. The two windings in the phase A are in series, so they carry the same current. Suppose that for that specific arrangement, the current flowing this magnetic material generates a south pole on the stator here, on the top, and a north pole on the stator at the bottom. So the, say, equilibrium position for the rotor is having the, oh my god, I don't know. Is here? Yes. The equilibrium position is having the north pole of the rotor close to the south pole of the stator, and the south pole and the north pole here are attracted. Okay, so if you want, this is the equilibrium position. Now, if you do not excite the phase A and you are exciting phase B with a current entering B in this way, suppose that for arrangement I generate a north pole here on the left and a south pole on the stator on the right, then what happens is that I have 45 degrees clockwise direction rotation of the rotor in order to align the north and south pole in this way, in the way shown in the phase B. Okay, so what happens, what I need now to have another 45 degrees clockwise rotation, that means that I need to excite a, let's say, north pole on the phase A and a south pole on the bottom here. So a situation which is opposite to that you can find in the part A of this figure. Okay, in order to get another clockwise 45 degrees, I have to reverse the direction of the magnetic field of the north and south pole generated in the stator. But this can be done, say, reversing the direction of the current. If the current is not entering A, but is, say, exiting A, okay, the currents flow in an opposite direction. If you apply the right-hand rules, now the direction of the north and the south pole has reversed. But this is exactly what I need to get N on the top and S on the bottom, making 45 degrees of rotation. Again, phase A is not excited. Phase B is excited with a current that now is not entering B, but is exiting B. Now we get, let's say, the situation that is needed for another, say, 45 degrees of rotation. Okay, which is our step angle is 45 degrees. Alpha P is 45 degrees. 45 degrees that can be derived by an equation which is similar to that of the variable reluctance mode. Is the total angle 360 degrees divided the number of poles in the stator, so the number of phases that are 2, and the number of poles you can have in the rotor. Sorry, I said always 45 degrees, but it's 90 degrees. Sorry about that. No one of you complain for this. Okay, of course, when you change from phase A to phase B, A and B part of this graph, okay, the rotor experiences a rotation of 90 degrees, okay, from vertical north-south to, say, horizontal north-south direction. Sorry about that, but it happens in the last lecture of this before the break, the Easter break, okay. So alpha P is 90 degrees. So yeah, you have 4 steps in a complete revolution. Okay. Questions, doubt about this mechanism? This mechanism does not involve the reluctance torque. It's just, say, alignment of north and south pole due to the permanent magnet in the rotor. Okay. This table again show you the difference you can have for one phase on mode. That is exactly the description that I provided you before. Okay, 90 degree stepper motor, permanent magnet, 2 phase on, exactly the same description I had before. I'm exciting 2 phase in the same simultaneously, in the same instant. For example, I exciting A and B, okay, providing you 45. The minus in this table means that the current is not entering the node A, but it is exiting. Okay, so we have to pay attention to the direction of the current in order to get the correct and continuous alpha step movement of the rotor. Okay, and then you can have also, again, as in the variable reluctance motor, the possibility to alternate 1 phase on and 2 phase on modes in order to have the alpha step mode that has exactly now, this is true, 45 degrees as alpha step. Okay, so we have 8 steps for complete revolution. Okay, so this discussion basically is the same. The only difference here is that the rotation, okay, the position that you can have depends on the direction of the current. Okay, if the current enters or exiting on the phase, now it has a huge impact on what happens on the rotor. Okay, this is not the same for the variable reluctance motor, which rotation is totally independent on the current direction, only depends on the direction of the magnetic field which is excited by that current. Okay. Now there are a few slides about some implementation of this principle, which provides you fine resolutions of less alpha p, and that are say basically most of the time implemented when you have permanent magnet stepper motors. Okay, just an overview of this solution. This is called the Clopol's permanent magnet. Is a way to, let's say, implement this permanent magnet circuit. The construction is a little bit complicated, but the as a say general remark, the operation principle is basically very simple. In that solution, we have the rotor, you can see here, cylindrical type. Then you have a permanent magnet embedded there, but the permanent magnet has embedded in such a way to have several north and south pole alternated. This is basically shown in this drone here. You can see here there are and south vertically placed. They are permanent magnets all around the external surface of the rotor. Okay, there are a lot of these say bar magnetized in this way. Then you have two coils. Okay, the stator now has basically two coils. As you can see, one is powered by this yellow and red one terminals, and this coil is surround the permanent magnet, and the other one is powered by these blue and green wires. Okay, and this plays in the say lower part of this construction. It's called coil A and coil B. So we have the rotor with this part. There are two coils excited here. Then the stator is made up of this very strange construction that is called claw poles. Okay, as you can see here, there are these teeth. There are some trapezoidal teeth here that intersect one to the other. Okay, like here, top, and then on the other top here. Maybe is something much clearer in this picture here. You can see this strange construction you can see here. Okay, so this is the basic construction. Then, which is the operating principle. Okay, so the coil A and coil B are exactly these two. This is a schematic, which is, let's say, simplifying the description. Okay, as you can see, the magnetic material here is shaped with these claw poles, say trapezoidal claw poles that intersect one to the others for the coil A and the coil B. Okay? These are, say, these parts here for the coil A, and these are for the coil B. And this is the coil running around this. And these blue and red parts, this bar vertical, are exactly the permanent magnet in the rotor. Okay, so when you excite, for example, coil A, and according to the arrangement, you can have a south pole on the top side, on this top teeth, and a north pole on the, say, bottom teeth here, you are alternating south, north, south, north, south, north on the stator. Of course, the rotor is commanded to align itself with the polarity of the rotor or the stator. Okay, so in that condition, for example, the south red bar will be aligned to the north one. Okay, so as a movement that is in direction toward left, we can say. When we excite coil B and not coil A, note that you have the same, say, the current flow is in the coil, that you have south and north pole, but the pitches here, so these claw poles, trapezoidal claw that you can have here in the stator of the coil B, are not aligned with the stator of the coil A. They are, say, in between the south and north. Okay, the south here is in between these two. This provides half pitch is called half pitch. And so when you excite these, the start, for example, the yes, you have another further movement, for example, align the position of this quantity here to the next poles. Okay, will be excited in the correct way. Okay, this is also indicated here with a different way, but again, is a typical construction to, let's say, increase the number of total number of steps for complete resolution. Okay, is a very the specific way to make permanent magnet having very high resolution. Okay, because now the resolution depends on the number of teeth you can have in the stator, in the claw poles. Okay, you can reach, let's say, less than 10 degree of alpha P. You can find several videos on YouTube illustrating this behavior. It's very funny to do, but basically the operation is not so complicated. Okay, so this is a summary of the permanent magnet, illustrating that basically the resolution range is from 7.5 degrees to 90 degrees. Okay, typically they have also a problem with respect to the variable reluctance that is called the detent torque. What is the detent torque? Suppose that you have in this case basically in the variable reluctance motor, when you have no currents flowing into the in the stator winding, the rotor is free to move. There are no rest position for the rotor. Okay, so you can have, let's say, no current flowing into the stator, and the rotor can move, say, freely, no problem. Here, there is a problem due to the magnetic materials of the permanent magnet, that even in the case you have no currents flowing into the stator, then you have to overcome a specific torque to move the rotor, even if you have no currents. This is called the detent torque. Okay, so this can be a problem somewhere, or sometimes it can be exploited for some application. Okay, for example, for holding a load when the motor is not powered. Okay, if the motor have a large detent torque, they can be, say, exploited. Typically, the permanent magnet motors have a large inertia due to these, say, problems of the magnetic material, slower acceleration with respect to variable reluctance motor. Then I want to discuss a little bit the hybrid motors, just not so deep discussion, but this is the third class of stepper motor that you can find. Hybrid motors typically are, say, something that includes both the permanent magnet and the variable reluctance motor. Here you can see a picture showing the construction. And in deconstruction, you can see that are basic elements that comes from the variable reluctance motor. For example, the rotor has a shape, has teeth. And this means that you are, say, also exploiting the variable reluctance torque. But you have a rotor which has these teeth, but the rotor has also permanent magnet embedded. The permanent magnet are embedded in order to create a longitudinal north and south pole. So in this direction, this is the rotor shaft here. The north is on one side and the south pole is another side. Okay, is a little bit different from that I explained to you here, in which the north and south pole are, let's say, radially. Okay, this is the cross section, and in this cross section you can see that the north is, let's say, on one, say, side of this cross section. The south is another side of the cross section. In the hybrid, the north and south pole are longitudinally embedded. So here you have the north and you have the south, for example. There is no radial variation. In each section, you have north and south pole. Okay, but these now north and south pole are, say, radially, are longitudinally displaced. This is the section of the hybrid motor. Okay, you have two sections now. One is one end, the left end. Another one is the right end. Here you can see there is just north pole, and you have just south pole, because this is the permanent magnet. And then you also have teeth here. Basically, if you excite the phase A, what happens? Another important construction feature is that, look also in this picture here or here, when you have a teeth in one end of your rotor, this corresponds to a valley in the say, construction in the longitudinally separated section. Okay? They are not aligned, the teeth of the two, say, cap you can have in this termination. Okay, so they are, say, when in the space between two nodes, you have a south. Okay, this is the basically construction. But anyway, you have your stator, two phases here. So if excite, for example, the phase A, in that case, you have alignment with the north pole here, north-south, and then the other ends, you have here the south in between the two nodes, which is aligned with the north pole. Okay, basically this is the mechanism of generation. The step angle is given by something which is related to the difference that you can have in the number of number of phases, which is, say, the number of stator 4 is the number of the stator expansion, if you want, and n here 5 is the number of rotor expansion. Okay? And so due to this mechanism, which is due to the fact that the two pitches are, say, half pitch shifted in two of the hands, you can have, say, you can increase the resolution. Of course, this is for one phase on mode, etc. You can also get two phase on, etc., etc. But anyway, and then it's just one possible construction. You can have a more complicated construction, like this, for example, that helps to increase again the alpha p, to reduce the alpha p, increase the resolution. Or then you can have some very strange construction. You can have permanent disc magnet. The solution are very wide, and typically the fantasy in this field is no limited. There are very genius construction you can see on the internet or in the specific literature. Okay, this is a comparison table. And this is a collection of some applications that you can find for stepper motors, from printer, then you have the tooling machine, some hydraulic applications, projectors, etc., etc. You can find in several different applications, from photography, for example, for the digital camera focus, zoom function, medical scanners, etc., etc. So just now, this is the basic discussion about the way this kind of models operates, the basic principle function. Okay, if you have questions about this, I can answer. Okay, now just say have a transition. Let's have a transition from this mechanical side to what is more interesting for us, which is the how to drive this motor to get specific performance. Okay, and so in order to do that, I want to just summarize some specific characteristic of the motors, just listing what you can see in a data sheet. Okay, as I said, there is the Holden torque, which is the maximum static torque that can be applied to the shaft without causing a continuous motion, because you have, say, equilibrium position, so the rotor find a rest position, for example. The 10 torque is something which is related to the permanent magnet stepper motors, okay? And this is due to the fact that you cannot have continuous rotation when your motor is unexcited, okay? Rest position is a position which you have, say, the rest of your rotor. Step position error is something that I already explained due to the presence of a load and the characteristic of the torque generated by the motor. Something which can be useful is the stepping rate of pulses. I said that a basic unique feature of the stepper motor is the fact that you can have a one-to-one relationship between the rotating speed and the frequency of the motor and the frequency of the pulse you apply the input. Okay. Sometimes this can be expressed in frequency, so in hertz, or maybe you can express in say in a different say you can say unit, which is the revolution per minute. Okay, and the revolution per minute is something that can be useful you can find in datasheet. Okay, and this relationship n equal 60f divided by s, giving you the relationship between the rotational speed, so in hertz, and the revolution per minute of your rotor. But what I want to discuss a little bit here is this curve, okay? Because this curve can be different according to the way I drive the motor, okay? Something which is related to the electronic circuits driving the motor, okay? So let me just showing the whiteboard. Okay, I want to describe this curve, which is something that you can find in datasheet of stepper motors. Okay, something which is always provided by manufacturers. You have a graph which you have the let's say let me call the pulse frequency. So it is the frequency by which I applied pulses on the input side of my driver. Okay, sometimes it's called PPS, which stands for pulse per second. And then you have here on the vertical the torque. Typically there are two curves. One is this one, and another one is like this. Okay. When I have 0, means that I have not providing any frequency at the input. Okay. The maximum torque you can have here is the holding torque. This value here. Then you have two curves. The blue one, let me call it blue, is called the pull-in curve. The red one is called the pull-out curve. What is the meaning of the pull-in curve? The pull-in curve shows the maximum stepping rate, PPS, for different values of the load torque that you can have here, at which the motor can start, synchronize, stop. For example, suppose that the load torque is TL1. I have this point, blue, okay, and so I found a speed, a pulse per frequency, pulse per second, that is S1, okay. So it means that the stepping rate can be increased, let's say, from 0 to here without any problem, because this curve is related to, let's say, what happens when you stop your motor. When the motor is running for the same TL1, now the speed can be increased from S1, let me change the color, to S2. It is the intersection with the red curve. But if I increase suddenly from 0 to S1 with the motor which is, say, stopped, then I get problems. I lose my synchronism. Okay, so what is the maximum, which is related to the slowing range? Remember, I said that you have there is no way to suddenly increase the rotational speed of the stepper motors from a motor which is say stopped up to a certain value, because sometimes it loses the synchronism with the number of steps. Okay, this curve is completely exactly what I'm intending in that situation. The blue curve is providing you for any given load the maximum speed, the maximum pulse per frequency you can obtain, you can employ for starting a motor from 0, or the same way from, say, from a specific speed to get to 0. Okay, the reverse is always. The red curve means that when the motor is running, then you can increase the speed from S1 to S2. So the difference between the red one and the blue curve is exactly what I previously defined as the slewing range. The slewing range is the region of the pulse per second frequency of the input, say, signal, that makes the motor rotating in between of these two curves. Okay. If you are, for example, at S2, you cannot decrease from S2 to 0 suddenly without going to stall. We have to first decrease your speed from S2 to S1, and then from S1 you can, say, decrease to 0. Okay, these two curves are typically provided by the manufacturers, depends on the construction, the characteristic of the motors, etc. Okay, and this is what is indicated here. This is a graph that is related to measurement provided on some stepper motors that show you the pull-out torque. Okay, here is in millinewton per meter. Okay, as you can see here, the pull-out torque, there are 3 different pull-out torques. Sorry, there are 2 different pull-out torques. One is the black curve here, and one is the light green curve here. Okay, because for the same motor. Okay, why you get these 2 different pull-out torque? Because you are using 2 different different electronic circuits that provides the steps for construction, for rotation. For example, the blue curve, the black curve is obtained by a specific integrated circuit which is called 3770 here, and the light curve here is due to the another driver which is called L over R. In the L over R, you can see that my pull-out torque provides not a useful torque, is concentrated with very low stepping rates. With another circuit, okay, you can get the same torque, for example, 50 millinewton per meter for value of frequency which is much larger. Okay, and of course this can be important. Okay, obtaining a much wider pull-out torque, because it means that I can increase the speed of rotation, having simultaneously a large value of the torque developed by the motor. Okay, so this can be quite dependent on the way I drive the motor. And of course, other parameters you can find in datasheet of stepper motor is the electrical characteristic of the winding you can have. Okay, and typically they are always indicated in terms of parasitic resistance. Okay, indicated the ohmic losses, omega, between 0.25 ohm and 100 ohm, or you can also the inductance of the winding, 0.5 millihenry to 100 millihenry. Depends, all these parameters depends on the motor side, etc. And also the nominal output power. So in the next week lecture, okay, which is Thursday 8 at 10, now we dive into the construction of this driver, okay, and we'll see which way this pull-out torque will be affected by the driver circuits. Okay, so we move from the just mechanical operation principle to something which is related to the way I have to drive stepper motors. If you have questions, of course, I can answer your questions here or maybe later when you're studying this topic. If you have no question, I wish you a good Easter to you and your family. We will see next week, Thursday of the next week. Okay, guys, no questions. So see you. Bye. Have a nice Easter.